In class, we introduced quantum numbers and discussed Schrodinger's equations and Heisenberg's equations and Broglie's analysis that electrons can exist both as particles and as waves and have wave properties. We're going to take a closer look at the quantum numbers in this video and what do they mean and how can we relate them to areas of the periodic table, because much of this information can be gleaned from looking at the periodic table and the patterns that it shows. The principal quantum number tells us a range of energies for a specific energy level. So unlike Bohr's model where we have an energy level representing an orbit, for us now an energy level is an area of probability that represents a range of energies for electrons in that energy level. The principal quantum number helps determine what the relative size of the area of probability is. The larger the energy level, the larger the area of probability for those electrons that exist in that energy level. For example, the second energy level is going to be have a larger area of probability than the first energy level, but it's going to be a smaller area of probability than the third energy level. The last thing is that the energy levels are represented on the periodic table by the period numbers or row numbers. So if you numbered the periodic table starting from the top down on the left-hand side, you would simply be representing what the highest energy level is for those atoms in those periods or in those rows. Now remember, this isn't some of them may have electrons in the lower energy levels, but these are the highest energy level represented by atoms in the ground state for those elements. The second quantum number that we're going to look at, we're going to call the sublevel quantum number. And for all energy levels except for the first, they have multiple sublevels. And the number of sublevels on each energy level is represented by how many or what the energy level value is. A sublevel is simply going to be a smaller area of probability within the energy level. And again, throughout this, we're going to be talking about areas of probability. Now, each different sublevel is going to have a different shape or structure to it. And they also have a certain amount of energy associated with them. So not all sublevels within an energy level are going to be the same energy, but they will have similar energies associated with them. As I said, the number of energy or sublevels within an energy level is going to be equal to the value for the energy level. So if n is equal to 3, it will have 3 sublevels. If n is equal to 10, it will have 10 sublevels. For us, there are only 4 sublevels that we need to describe atoms on the periodic table that exist naturally. There are more sublevels, but we really only need these 4. The 4 that we use have letter designations associated with them. S is going to represent a sublevel within an energy level that can hold 2 electrons. The P is going to represent an area that can hold 6. The D sublevel is an area that can hold 10, and the F sublevel is an area that can hold 14. Now, each sublevel is represented on a periodic table by different sections, and this will become clear as we look at the next quantum number as well. But the S sublevel is represented by groups 1 and 2 on the periodic table, as well as helium. The P sublevel is represented by the 6 columns to the right on the periodic table. The D sublevel is the shorter area that has 10 columns, and the F sublevel is represented by that area that's kind of separated to the bottom of the periodic table. Again, each one of these represents an area within the sublevel or within the energy level that is a subsection of it. The third quantum number that we're going to look at is the orbital quantum number. And each sublevel is itself subdivided into smaller areas of probability, which we call orbitals. And those orbitals within a sublevel are going to have the same amount of energy. So if you have a P sublevel, and as we will see, it's made up of 3 separate parts, each one of those parts is going to have the same amount of energy within that P sublevel. Each orbital can hold 2 electrons. And this is one of the reasons why we have the number of columns in each area of the periodic table. Now, we don't have a specific section designated for the orbital quantum number. But like I said, the number of areas on the periodic table, or number of columns within each of the sublevels, is driven by this number, the number of orbitals that each sublevel can have. For example, the S sublevel has one orbital associated with it. Since each orbital can only hold 2 electrons, that means that the S sublevel is going to have 2 electrons total. That's why on the periodic table, the S sublevel is represented by only 2 columns. The helium would be included as that second column. The P sublevel has 3 orbitals that make it up, for a total of 6 electrons. That's why groups 13 through 18, those columns, are going to be consisting of the P sublevel. The D sublevel has 5 orbitals. That means it can have 10 electrons total in it, and that's why there are 10 columns in that shorter area of the middle of the periodic table. And last, the F sublevel has 7 orbitals, which means it can hold a total of 14 electrons, and the section that's lower at the periodic table, designating the F, is going to have 14 columns. So these quantum numbers describe the areas of probability for the electrons. They give the electron kind of its address, its home in the atom. Remember that it is not a specific location but an area, and that the properties of the elements are driven by the electrons and where they are located. And that's why on the periodic table we have the patterns we do, because of how the electrons are organized in the atoms.